Okay, we have a lot to cover today, so I'm going to go ahead and jump right in. Thank you, everybody, for joining, making, moving, and managing millions of embeddings. My name is Amanda Wagner. I am the Senior Community Manager here at Pinecone, and we are absolutely thrilled to have you. For those who might not be familiar with Pinecone, Pinecone is a vector database that makes it easy to build high-performance vector search applications. Now, before I kick it over to our incredible hosts, we do have a few housekeeping rules. Number one, we ask that you use the chat for chat. Feel free to introduce yourself, say hi, but we ask when you have a question, and we hope you have questions, please add them to the Q&A portion of the Zoom. We reserve roughly 10 to 15 minutes after every event for your questions, and so this helps us keep organized and answer as many as possible. If you miss something, do not worry. We record all of our events, as I'm sure you heard at the beginning, and we send them out post-event. We also share all of our recorded events on our YouTube channel and our social media. So if you are not subscribing or following, I highly suggest you start today. If you have questions after the event, you can email me personally, and I will serve as your inquiry liaison. And you can reach me at amanda@pinecone.io. Now, when we send out our recording, we also add a survey. We would love your feedback to help our events grow, become more poignant, and feed you in the ways that you need to be fed. So fill out that survey, give us that feedback. Without further ado, I'm going to let our fabulous host from Databricks introduce himself. Nitin, why don't you tell the crowd a little bit about yourself?
Yeah, hi everyone. My name is Nitin Wag. I am lead ML product adoption specialist at Databricks. And I'm passionate about helping our customers take their ideas from machine learning ideas from inception to production, and also accelerate their machine learning journey with our lakehouse platform. So I'll be talking about it. This is a super exciting topic. And I've seen embeddings being used in many workloads, and super thrilled to partner with Pinecone in the journey. Roy, or to you.
Thanks, Nitin. I'm really excited that you're joining us today. Today I hope to talk to you guys about how Pinecone and Databricks are working together to facilitate the process of creating embeddings at scale, from millions to even billions of embeddings. I've personally really enjoyed using Databricks for many years now, and I've really found it to be very helpful in creating embeddings at scale here at Pinecone. So just let me start by sharing my slides. Okay, I think that's good. So let's just quickly go over our agenda for today. We'll start with a quick intro to Pinecone for any of you in the audience who isn't yet familiar with us. Then I'm going to describe the challenges of dealing with vector embeddings at scale. And then I'll hand it off to Nitin to talk about Databricks, their machine learning offering. And after that, we'll start discussing the solution architecture that combines Pinecone and Databricks' capabilities. We'll walk through a short demo that I created ahead of time that kind of shows the implementation of high-scale embedding, a high-scale embedding pipeline. And of course, like Amanda said, during the session, please share your questions in the Q&A section, and we'll do our best to answer them at the end of the session. So let's get started with a quick introduction to Pinecone. So I know some of you might not know what Pinecone is. Maybe you've joined here because you're interested in Databricks and what they can do with embeddings. So I'll just walk through this very quickly. I'm assuming maybe a lot of you do know what Pinecone is, so I'm just going to keep it short and sweet. So what's Pinecone? Pinecone is a fully managed high-performance vector database. And why do we need a vector database? Well, we want to efficiently store vector embeddings and then be able to query them and update them and then delete them if we need to. So control the full life cycle of the vector embeddings. We want to be able to scale our vector indices with ease. So we don't want to manage that overhead of dealing with scaling a handcrafted vector index. We want the data ingestion of our vector embeddings to scale as our data grows. So this is a pretty big challenge that is being solved by again, both Databricks and Pinecone working together. And we want to ensure that when we're querying and interacting with these embeddings, we're ensuring a low latency and optimizing the cost of our interaction. This is an overall architecture for a typical application that uses Pinecone. So you typically see two phases, one that takes content and basically interacts with the embedding model, then creates vector embeddings and stores them in Pinecone. And then the second phase is going to be the application encoding its queries, then basically taking that encoded query and querying Pinecone to then respond with a query result. And that's the long and the short story of what most typical applications do with Pinecone. There are, of course, many use cases ranging from semantic search to recommendation, to recommenders, image search, question answering. I'm sure many of you've seen bots and whatnot. But there's also fraud and anomaly detection and many more use cases that we're seeing and definitely seeing them in use with Databricks. And if you want to learn more about these use cases, please be sure to head to our website where you can read a lot more about these use cases. I want to kind of like double click on a specific example of semantic text search and to see kind of like how this process works. So as you can see on the left side, we have a query that comes in and encoded. On the right side, we have documents that are coming in and being encoded. Then we perform a cosine similarity operation, basically based on the cosine similarity of the vector embeddings from both the query and the document. We can produce a relevance measure that then gives our user a relevant result that encapsulates the meaning of their query. And goes beyond just plain keyword search. So that was the long and the short of what Pinecone is and what it does. And now let's talk about what is challenging about dealing with vector embeddings at scale. So generally speaking, we can say that generating embeddings is a very compute intensive and so time intensive and cost intensive process. For every piece of content that we have, whether it's image or text, we basically have to hit up an embedding model and get the inference out of that embedding model. And if you've ever tried to do that, you know that process takes time and actual compute resources. When we are dealing with big data pipelines, we need to make sure that the data coming in is sanitized. So if we have text or any kind of structured content or unstructured content, we want to make sure that like the pipeline is properly sanitized. Once we create our embeddings, we want to make sure that we're storing those in a store that is capable of dealing with a huge load of embeddings so that we can query them in our application. And at this big scale, run-of-the-mill indexes like face, for example, just won't do the trick. When we're dealing with hundreds of millions and billions of embeddings, we just have to look for a different type of architecture. So our store also has to be able to ingest these created embeddings very quickly. So we can't have that process take a very long time. Otherwise, our data pipeline won't be very performant. So the bottom line here is that handcrafted architectures where you have single machines or even pipelines that are put together with scotch tape are not just going to scale. And that's exactly where Databricks comes in. It allows us to kind of build a more robust pipeline for these types of processes, and that's kind of like why we're all here to discuss and to see how it works. And at this point, I want to hand it off to Nitin to talk a little bit about Databricks for machine learning. Nitin, take it away.
Yeah, thanks, Rory. Awesome. Again, hi, everyone. So I have only a few slides, I promise, and then I'll hand it back to Rory for like a really awesome demo we have built together. I'm sorry, which slide? Right. Yeah, can you go to the next slide, please? Right. Awesome. Yeah, so before I get into like the nitty-gritties of machine learning, I want to quickly talk about our Lakehouse ML platform, or Lakehouse platform. So with Lakehouse, which is sort of our de facto platform that is multi-cloud, you are able to have all your data structured as well as unstructured in one place. You can just use your cloud storage. If you're on AWS, use Amazon S3. If you're on Google Cloud, Google Cloud Storage, or Microsoft Azure, Azure Storage. Now, you then bring reliability and extremely fast query performance to that data without leaving the lake with our open source technology called Delta Lake. Now, Delta Lake sort of provides a tabular representation on structured or unstructured data. And then you can simply use that data across multiple of use cases that are here, right? Like data warehousing, data engineering, data streaming. So you're looking at a single source of truth or single data layer. Now, next, there's Unity Catalog on top of it, if you look at the diagram, which provides governance for all the data assets, all the models, all the source code that you have, so that you have a unified governance right within your enterprise. And then we offer purpose-built tools to allow everyone to collaborate on the same data, which is amazing, right? So let's say you have a data analyst who's probably, just want to query on that data. You have data engineer who may want to like do data engineering, ETL pipelines, and then you have data science and machine learning folks like data scientists, ML engineers. So all of them are looking at same set of data, and it's all unified within your enterprise. Now, what are the advantages, right? So first, you have dramatically simplified your data architecture for all of your workloads: data warehousing, data science, ML, as well as data engineering and data streaming. One of the cool component, as we are talking about embedding, is what we call as DLT, Delta Live Table. It's an amazing way to sort of simplify your data engineering pipelines, similar to like SQL. It has like SQL-like syntax, and it simplifies your data engineering pipelines for batch or streaming use cases, which is super useful when you are talking about embeddings, because embeddings can come through like some sort of clickstream events. It can come through, like the source for embeddings can come through some batch uploads. So DLT is amazing. It is our streaming capability. Now, second, the entire platform is built on open source and open standards. Of course, Databricks is known for optimized Spark, but we have many other offerings also for data science and machine learning. This means, so we have MLflow, we have Spark, we have Delta, and most of the capabilities that Databricks offers are also available in open source ecosystem. This means you have a lot of freedom in how you evolve your data strategy without walled gardens restricting present and future choices. Very important. So there's no lock-in. And not to mention the vast community of talent and that resides in the open source community. And finally, you get one consistent experience across all clouds. 80% of enterprises will or are looking to use multi-cloud strategy. So you have like a single solution, so you don't have to reinvent wheel as you probably move between those clouds for your data and AI strategy. Next slide, please. Give me a second. Yeah. Yeah, so before I dwell into like individual components of machine learning, this is a view of our lakehouse ML or our machine learning capabilities. So as you can see in this cake, Databricks machine learning is built on top of two most of the successful open source projects in the world, Delta Lake and MLflow. Now, Delta Lake is, as I said, it's a high performant storage cache, and then MLflow is a leading MLOps tool, downloaded almost 30 million times a month, massive. And then Databricks provides a managed MLflow. Now, from the top, you have these collaborative multi-language notebooks, or what we call as IDE environments. These are well integrated. You can use Python, Spark, R, SQL, any languages. So they are sort of multi-language as well, and they are collaborative across data scientists. Then you have AutoML capabilities for simple regression or classification model training. If you are just new to ML, or if you just want to generate like code for your feature engineering, that you can take it to your ML model. So amazing glass box algorithm, which not just gives you models, but it also gives you the code that is underneath the models. And then you have like these slew of capabilities, right? From left, you have data prep capabilities, and then you have feature store capabilities. Then we provide ability to build different types of models in different ML frameworks. And then once your models are trained and tuned, then you can serve those models or take them elsewhere. Okay. Next slide, please. Now, one important aspect as we talk about embeddings, because embeddings are generally used in like sort of deep learning use cases. Majorly, I mean, they have application across the board, but deep learning is probably where we use a lot of these embeddings. Now, with Databricks, you get these Databricks machine learning runtimes. So these are just, you can imagine, these are optimized and pre-configured machine learning frameworks, right? So you get all the necessary packages, Conda, as well as frameworks like PyTorch, TensorFlow, Scikit, all within these runtimes. You just select the appropriate runtime version, and you get underneath, you get the underlying, let's say, PyTorch framework version or TensorFlow version. So super easy. You don't have to install any libraries. Then second category is if you're doing advanced ML, you may need to do distributed ML. So we support, of course, Horvath, which is an open MPI-based distributed framework. Of course, there's a Spark ML where you can distribute a lot of the classical algorithms. Then we have contributed to TensorFlow distributed. So there's this PySpark wrapper around TensorFlow distributed. Literally, you can bring your TensorFlow code, and we will help distribute that across multiple GPUs on single instance or multiple instances. And soon we'll be launching PyTorch distributed, which will be a contribution to PySpark. And then we have recently, last week alone, we launched Rayon Spark, which is amazing. If you are into Ray community, now you can also run Rayon Spark and leverage, for reinforcement learning or other type of use cases. If you hyperparameter tuning is super important for a lot of the use cases. So we support HyperOpt as a library. So we have sort of contributed to HyperOpt, created a wrapper in Spark, and then that's our mechanism to fine-tune your models for, let's say, neural architecture search or hyperparameter search. And finally, we, of course, support all types of instances, like, of course, all the CPU as well as GPU instances across all three clouds. Okay. Next slide. Now, once your models are trained and tuned, MLflow helps you sort of productionize those models, track your experiments. So let's say you, as a data scientist, you want to start working on a new use case. You just add like few lines of code, import MLflow, add few lines of code, and it'll start sort of tracking your hyperparameters, tracking your metrics, artifacts, and metadata, and it is all available in a single pane of glass in MLflow experiments tab. Now, as you sort of evolve that model is not like a singular thing, right? it's done and dusted in a single try. You may experiment more with the model by changing hyperparameters, getting different types of accuracies and metrics. So MLflow also tracks all those runs automatically. And it also gives you a really nice API that you can just call like TensorFlow or PyTorch API, so that you can save that model directly within that format. And it's not just saves or pickleizes the model, but it also like register all the dependencies that are within the model, like runtime, libraries, etc., as well as the input and output specs. And then once you are satisfied with the model, you can then register it in MLflow registry, which is another open source component. It's really great way to like hand off your code between data scientists and data engineers, because MLflow registry gives you all the model specs, like model artifacts, evaluation metrics. It also gives you a sort of like input and output specs. So your ML engineers do not have to really ask data scientists. It's all in there. And then with model registry, then you can promote that model between, like a challenger champion concept. You can promote between different stages, staging, prod, and you can also define versions of those models. Once the model is registered in MLflow registry, you can then, of course, use serverless real-time inference capability that we have recently previewed. It will be soon GA on AWS and Azure. And so with that capability, it's a one-click deploy, and the model is available for, of course, real-time inference. You can use that same model for batch as well as streaming. So all three modes of model serving are available. Or if you want to take that model to your own platform or like on edge, the model is there. You can just, MLflow gives you a really nice package that you can directly deploy on some sort of EC2, some sort of instance, VM instance, or as well as a container. And then MLflow allows you to sort of monitor and manage entire lifecycle of that model for MLOps. Awesome. So that was all my slides. I will hand it back to Roy to walk you through this amazing demo.
Thanks so much, Nitin. That was awesome.
Thank you.
So let's dive into our solution architecture now. And first, let's talk about how Databricks and Pinecone kind of mitigate some of the issues that we've mentioned before. So we talked about how generating embedding is compute intensive, and this is exactly the reason why we're using Databricks to parallelize the compute effort and kind of manage it end to end. Of course, we mentioned data sanitization, and there we're going to leverage Databricks' Delta Live tables. Like Nitin mentioned, it's an immensely helpful tool that ensures that we have controls over every step of our data ingestion pipeline to make sure that whatever goes into the embedding step is actually the data we really want to embed. And we have control over the details of what qualifies as good data and what doesn't. Continuous processing is complex, and I think I might have missed that point before. But making sure that this process is continuous and sort of is streamed end to end, that's not an easy thing to do, but it's really a breeze with Delta Live tables as well. Storage and query of these vector embeddings at scale, that's what Pinecone is for, right? That's of course what Pinecone offers, and that's what we focus on. And we need to make sure that the embeddings are written from Databricks to Pinecone quickly. And that's why Pinecone created a connector that is very, very efficient in writing large scale payloads in a very short amount of time. And I'm going to show you how that's done in a moment here. I have this architecture diagram here that kind of like will walk us through what the demo that I'm going to show is going to do. So we start with a raw data store. So this can be S3, a Hive table, or a combination of any of the data sources that can actually be consumed by Databricks by a read stream call, which you'll see in a moment here. You can imagine a process that continuously writes to this data store, and then Databricks picks that data store up with a streaming process. And there we basically apply a set of transformation to prepare that data for embedding. And you'll see in our case, it's going to be basically taking a set of documents and exploiting them into sentences that can then be embedded. We then use an external embedding model that is brought into Databricks to embed the content. We write those embeddings into a Hive table, and this is also part of the Delta Live table pipeline. And then after that data is written in a separate schedule job, we write these embeddings from our Hive table to Pinecone. And then when that's done, our application basically interacts with that embedded, with the embedding index through the Pinecone API. And that part is not something that we're going to cover today. We're not going to cover the application. We're going to focus on exactly how the embeddings are created in Databricks and how they're written from Databricks to Pinecone. So yeah, I think we got to demo time. I'm going to stop sharing this slide and I'm going to switch over to our notebook here. Just give me 1 second. Okay. Oh. Okay, Nitin, can you just confirm that the screen is shared? I just want to make sure that I'm not going forward with that. Okay, perfect. All right. So what do we have here? We're starting with an installation of some dependencies here. You'll see at the very top, I'm importing DLT. So this is data live table. This is telling Databricks to actually apply the data live table interface on top of this entire notebook. So every time the data live table decorator is going to be used, that's going to signal to Databricks that that resource is going to be part of that pipeline. I'm including in my dependencies, we have Torch, which is a required dependency, Transformers, which is the Hugging Face library. That's the embedding model that we're going to use. Another dependency that I found out that is required called Sentence Piece. We won't delve into that too much, but if you really want to know about it, you can talk to me after the session. Here we include our dependencies. So you can see, I'm calling auto tokenizer and auto model from Transformers. I have NumPy here and pandas, and of course some functions and types from PySpark SQL. And you'll see how that's used in a moment. So the first step that we're going to do is read from the data source. And that's as simple as calling a .readstream call, right, on a table that I've created ahead of time called multi-news. It just has a whole bunch of news articles and summaries that I found from Hugging Face and created and made into a Hive table. This could be really anything, right? So this could be an S3 bucket, a Hive table, anything that interacts with ReadStream. With a ReadStream call could be used here. And again, as this data source is updated, if we are using a continuous process here in data live table, every time there's an update, the pipeline is going to be triggered, and all the process downstream is going to be recalculated. So after we've created this raw stream table, and you'll see that the tables are basically automatically named after the name of the function that I've defined, I can read that that table again as a stream and continue operating on it as if it were a data frame. So I'm using a with column, and I'm adding a distinct UUID for every document that is generated in my that was generated in my initial Hive table, and I'm also dropping one of the columns that I'm just not going to need for this process. So this is You can think of this step as sort of a data sanitization step that's going to be required. And you can imagine that like there are many types of transformations that you could do here in order to make sure that like you're indeed processing the data that you want to process, and no more and no less. The next step reads from documents. So I've created a DLT table called documents. This next step in the pipeline reads from documents. And now I'm doing something a little bit more elaborate. So I'm basically taking each one of these documents and I'm splitting them, splitting that document with a period, which basically breaks them up to sentences. It's a very naive way of doing it, but it's enough for the purposes of this demo. And I'm basically turning that those sentences into rows. So I'm basically exploding all of the elements in the array that resulted in this split, and now they become their own singular rows. Now, in order to make sure that I have some reference from each sentence back to the document, I'm basically renaming the ID, which was the document ID, to document ID. So now I have a column that is called document ID that carries the document's ID, and I'm assigning a new ID for each sentence, so that when I'm saving it in Pinecone, eventually we'll have a distinct ID for the sentence and an ID that references back to the document from which that sentence came. Now we get to the meatier part of this process. So like here, I am defining a user-defined function, a pandas user-defined function, which will essentially create our embedding. And what I'm doing here is I'm already preparing my result to be ready to be inserted, to be written to Pinecone. So, and the way I do that is by defining the schema to include an ID. These 4 columns are required by Pinecone. So I need an ID, I need the actual vector, I need a namespace, which could be either an empty string or something that I define, and metadata, which you'll see how I'm going to use that in a moment. So this UDF, this user-defined function, takes a data frame, and basically it's going to go over every element of that data frame because it's mapping over each element. It's going to take the column that I'm interested in. This is the column where the text that I'm interested in is in. And if we scroll back, you'll see that I've created a column called sentence here, and that actually contains the text that I want to embed. Here I'm calling the model. So I'm creating a tokenizer from that model, and I'm instantiating a model. And this in particular, in specifically, this is the Almini LM L6v2 model. But this could really be any model, right? Like DaVinci or wherever else you might find on Hugging Face. And I'm basically creating the tokenized version of the input. So I'm taking this text. I ensure that this text going in is indeed a string. And then I'm passing this to the tokenizer. Now I have my inputs prepared for the model to actually create the embeddings from. This is the inference step. So this is like the most expensive step in this whole process that basically results in the embeddings themselves. And this is where I'm actually taking the last layer of that model, right? The last layer of the inference, because I don't want the actual classification of the model. I want just the embeddings themselves. And I basically flatten them, create a list from them, and now they become a vector that I could actually save in Pinecone. And then I return for each one of these rows, I return a new row that consists of exactly this structure where I have the ID, where I have the value of the ID from that data frame row. I have the vector that I created, which are the vector embeddings. I've decided to basically namespace this under the name of the model that I used to embed this. And then finally, I have the metadata, and here I chose to have the reference back to the original document that the sentence came from, so that when I make queries, I can basically say, okay, if I hit on a particular sentence, if I found a sentence that's similar to the query, I know what document it came from. And that's basically it for this user-defined function. And this is the last step where I actually run this user-defined function. And you'll see here, I take the step called sentences, which I created in this function, and I apply the user-defined function on each one of these rows that exist in that previous step. I'm grouping by ID. Essentially, this is a no-op, right? Because the IDs are the IDs are unique, but that's the best way that I found so far to do this efficiently and run this group map operation properly. I'm sure there are better ways to do this, but this was my best attempt at this. So let's see what happens when we actually run this process. And I've already done that ahead of time, just to save us a little bit of time, so that we don't look at a screen that's just running a huge query. And I ran this on 1,000 documents. And as you can see, we get a very interesting view where we can see each step that was completed, and how many entries were processed. So like, this is our first step, our raw stream step, our documents produced from that raw stream where we added the UUID. Then I've exploded these documents to sentences. So we can see that from 1,000 documents, we went to 102,000 documents. And then eventually that was completed in 10 seconds. And then eventually this very heavy operation of creating the embeddings for these 102,000 documents, we see took about 20 minutes. And one other cool thing to see here is that we can see exactly what happened through that process. And we can see that the process was running, everything was cool. And then Databricks automatically saw that it's going to need some more compute power. So it scaled up 10 executors from current cluster size of 1, and then achieved that, and then actually processed all of the embeddings in a very short amount of time. So you can imagine that this process will basically run continuously. And there are, if we go here to settings, you see that I have 2 modes that I can choose to run this process. It could either be triggered or it could be continuous. And then if it's continuous, it's literally going to keep running until it sees that there are new entries that are coming into the top of the pipeline, and then just keep running this until it completes running the new entries, which is incredibly helpful. And the final result of this, and this is again in settings, I'm telling the pipeline to write the final result into streaming embedding. So like, let's look at what that looks like. And this is, again, the data lake comes very handy here with all of its abilities to basically store and govern the data. So I'm going to just flip here to our Metastore. And here you see all of my tables with some of my previous attempts. And I can see that I have my embeddings here, and I can sample the data. And I can see that I indeed have my vectors with my namespace and my original document ID exactly as I expected them. And then the last step to go from Databricks to Pinecone happens here. So unfortunately, we can't have that to be part of the pipeline, the streaming pipeline yet. We're waiting for some added support for external dependencies on the DLT side, but we can basically schedule this process to take place as frequently as we want. So you can imagine we have customers that are already doing this, basically running this process every 5 minutes, every 10 minutes, according to their need. And basically, you can see here that all I have to do is read that table that I just wrote to, that embeddings table, and I basically am just writing that data in to Pinecone, just specifying my API key, my environment, project name, my index name, and just hit save. And we can see here that to save 102,000 entries took about 48 seconds, which is not bad at all. And here it is, our vector index with all of these vectors already inserted and ready to go. And to do that, all I had to do is basically define my cluster with the dependency, and I'll just run through that very quickly. I think it's this one. We can see here that I have my Spark Pinecone connector that is required for this little bit to work. So I basically installed that dependency. Once that dependency is installed, I can do exactly what I showed, which is to write the data to Pinecone, and the process is complete. And that is it. That was the demo for this process. And I think this would be a good time to open it up to questions, if there are any.
There are a bunch of questions. Yeah.
There certainly are. And if you're still thinking of a few questions, again, please add them to the Q&A portion. I see folks already are. But let's dive right in. We have a random question from Kevin. Kevin asks, but do you know of any music-related applications or projects that are leveraging vector databases at scale?
I do not know off the top of my head of projects that are doing specifically music-related things, although it's an amazing idea, and I'm sure it's definitely possible. I'd be curious to know if companies like Spotify and Apple are doing something of that sort. Nitin, if you know anything.
Yeah, definitely. Spotify is definitely doing that. I've just recently, seen that in the news article. So they are definitely using embeddings for the similarity search as you get these recommendations. Actually, I'm working with another customer, not in the music industry, but in the audio, like they're doing like a gaming detection using audio clips. And certainly they are using embeddings, ingesting similar architecture that Roy was showing, ingesting around 22,000 clips per second. That's massive ingestion, and it all happens through like events, and then embeddings are saved for similarity search for detecting events.
That's awesome.
Yeah, very cool. Mario is asking about the OP stack. One of the many attractive features of Pinecone and OpenAI is the ability to quickly be up and running with their APIs via REST. We're able to quickly generate dense vectors with OpenAI's ADA model and store in Pinecone. But if we wanted to take advantage of hybrid search, how can we do this? Is there a similar option out there for generating sparse vectors via a simple REST API?
I don't know if that has much to do with what we're talking about here. This is more a question about, sparse, dense. I'd be happy to take this offline to talk about exactly how that could be done. I don't know if that, again, I just don't want to mix and match kind of the topics that we're dealing with here, if that's okay. So let's table that one and take it offline.
Yeah, Mario, I'll actually capture that question and get back to you. Also, as a heads up, we have an event coming up. It's yet to be announced, but it's a version of event we just did on folks using OpenAI and Pinecone to build. So keep an eye out for that announcement. We have a Databricks question. From Joydeep. MLflow is the ML ops platform in Databricks? Question. Or Databricks has its own. What about Auto MI as well?
ML, yeah, Auto ML.
Yeah. So MLflow is sort of an OSS project. It's an open source project, but primary contributor is Databricks along with the community. And Databricks also provides a managed MLflow in its, on our lakehouse platform. It means you just sign into a MLflow, the Databricks workspace, and you get MLflow at no cost. And it is much more well integrated. But then you also have a choice to use your own MLflow from OSS if you choose to do so. But I think the managed MLflow provides you, like a no-touch quick start offering for managing your ML ops at scale.
Cool, super helpful.
And AutoML, I think AutoML is sort of it's a automatic, like sort of machine learning. It's a glass box AutoML capability in Databricks. It's meant for sort of, if you're like new to ML or you just have like simple regression or classification problem, even you're an advanced user, it's a glass box because it does like, feature engineering. It gives you like, tons of feature engineering pipelines. It does like model training, model tuning with ensemble of models and gives you like a leaderboard of models. If you don't want to use those models, you can at least use the feature engineering code, the whole model training code, and then make it yours and start with the experiment.
Great. And Rui, this is in particular or related to the demo. Can you give one real life use case example to correlate with the demo and how it's helpful?
Yeah, actually, Nitin mentioned this something like this to me. One of their customer, and I don't know if you want to name their name, has a use case where they take a set of images that are related to one of their products, to all of their product line. And in order to create image search basically on top of those images, they have to generate a bunch of embeddings for those images, right? So like we're talking about massive amounts of images for products that they have. So you can imagine product X, and I want to find a product that is similarly looking to that product. I'd have to like first generate a ton of embeddings for them, save those, and then query on them to give you a result. But yeah, like I can think of many different situations where you'd like to do this. You can think of fraud detection and anomaly detection as well, where like I would take logs or other types of textual data. For example, if I want to find malware or phishing, for example, right? I take a lot of textual data, create again embeddings from that, and then match that with either known malware that I found or an item that I found that I need to classify as either malware or not, and then find similarities between that data that I'm querying for and the known malware, known phishing that I've created embeddings for. So there are many practical use cases where the input is like a massive pipeline of a lot of data that's coming in very fast. And you can't just like rely on, again, traditional pipelines to deal with that amount of data. I hope that answers the question.
Yeah, and kicking it back to the demo, I think we had a few folks asking, and you did touch on this a bit, why are the embeddings written in Hive table?
Yeah, so there's a couple of reasons for that. So one is at the moment, there's no support for external Maven dependencies in the DLT pipeline, which means that I can't basically take our Spark connector from Pinecone and make that part of the DLT pipeline, and then like not have that checkpoint where I write data into Hive. So the mitigation for that is to basically checkpoint the data and have it written into Hive, and then Pinecone picks it up and writes that, and then another process, right, picks that Hive table up and writes it into Pinecone. But there's another reason, right? Like even if I was in a normal quote unquote pipeline where I'm not using Delta Live tables, we do want that process of creating the process of creating the embeddings is indeed pretty expensive, right? And so you don't want to risk the option that, like, you know, something happens in that process and then all of the embeddings that you created are just gone. So it's a good practice to basically checkpoint that data into a Hive table, to have that like written there. And if you need to, you know, make room for other data, if you don't want to save that data for a long time, delete it after you're done writing that data into Pinecone.
Yeah, I mean, it's again going back to if you're looking at the data warehousing concept, right? There's a bronze, silver, gold. So I think what Roy is showing is probably like a gold layer, where the embeddings are created. So typically you would, because if you have like a high processing system, events coming from Kafka, you want to land them somewhere, and data like lakehouse is perfect for that. Just that create a bronze layer, then you can then run the whole embedding creation as a batch job, because it can get expensive if you have to run it all the time. And then you sort of shove that into Pinecone for better indexing and search.
Yeah, I know. Thanks for Priyavan for telling me to revoke the API key. That's already been done even before I showed this, so I know that it was there. Thank you.
So what are the best possible scenarios to use embeddings for millions of documents except search?
So like I think I mentioned a couple, right? Like one of them would be, malware phishing detection, anomaly detection. If we don't include image search and semantic search, I can also, let's look at my, I'm going to cheat and look at my use case list, because I'm having a hard time picking up of my head. Yeah, so I mean, it is sort of a form of search, but question answering, right? Like where I'm taking massive amounts of documents and creating a question answering model from them as well. But I think that like really like the ones that we are seeing right in production, right, have to do with anomaly detection and other security related use cases, where again, like there are massive amounts of information that are coming in. You can imagine emails and known malwares and sort of known whitelisted software binaries, right? Like they can be embedded in all sorts of sophisticated ways. Those scenarios are definitely happening in production, and we have actual customers that are doing that, and actually using Databricks for that too.
And another application of embedding is also like probably, for your machine learning training, before you train a model, you can create embeddings, find the clusters that are sort of a little bit disparate. Otherwise, you can train your model on a lot of data, but if the data is very similar looking, then you are not going to get as much mileage, and then you will end up spending more compute. So you would rather create clusters using embeddings, and then get like proportionate samples from different clusters, and then downsample your data. So it's a great technique as well.
Jay has a question. Let's say I want to run a semantic search on millions of embeddings that are spread out across multiple Pinecone indexes. Unfortunately, each Pinecone call is set up for one index only. How would I perform a search without having to code a bunch of index orchestration and results processing logic? If this is unavoidable, what are some best practices to use? I'm assuming.
Great, yeah, that's a great question. So like I would maybe ask like why why would you want to have multiple indexes in the first place? The reason why I'm asking that is because when really like indexes have like mechanisms that help with subdividing the index very efficiently, exactly for the reason that you want to avoid having to search across indexes. So the short answer is no, there's not a really good way of searching across indexes, but that is because indexes are meant to contain a lot of quote unquote segregated data, right? So one way is, for example, using namespacing, right? So if you want, for example, if you have a bunch of users, right, and you want to have the data in the index basically separated by user, you don't want the user data to be combined and with other user data, then you namespace it. So basically you create a namespace per user, and then you make your queries based on that namespace, and then you there is no way to go wrong, and you can and you're basically making sure that your queries are incredibly efficient as well. The other way of going about it is using metadata, right? So Pinecone allows you to do very elaborate filtering on top of that metadata. There of course are performance implications on you know, if you have very high cardinality in your metadata, then any query would probably take longer than if you didn't have very high cardinality. And so both of these mechanisms, right, allow you to get like a very fine-grained sort of control of like how you separate your data out within the index, and then the index itself can scale up or down as you need it, right? And so instead of you really want to ask yourself, like, what is the reason, right, for creating multiple indexes in the first place if it can be avoided?
Great, thank you. And this is another one that gets kind of into the nitty-gritty of the demo. Anonymous wants to make sure they understand this correctly. In the Pandas UDF, in line 15, text equal str features. You can also see this in the Q&A to follow along, Rui. Features does not distinguish between the different rows in the sentence column. Is that correct? Does this have any effect on the decisions that need to be taken, or does str features return as many rows as rows in the Pandas DF?
Yeah, so the answer to that is that so because of this Pandas UDF is a grouped map operation, basically the function is running on every row. And what's happening in that line where you go when I have str features, is basically I'm ensuring that this is a string that the model is going to accept, and not a what's called basically the row is wrapped in a pandas wrapper, right? That isn't a string that the model is accepting, right? So for that reason and for that reason alone is basically being cast from that type back into a string, and it's just like a very superficial and not very interesting bit of code.
Okay, we're at time, but we've got a few short ones that I think we can dive through really quickly. So is it a norm to break up a document into sentences before generating embeddings?
Yes, because again, like you want to ask yourself, like, what is it that you want your users to find, right? Like what are they going to search for, right? And what is the similarity that you're looking for? Again, like if there's going to be a better chance of hitting, like if I'm searching for several words, right, I'm going to have a better chance of hitting a piece of a sentence, a portion of a sentence, than I do and hitting it accurately than I do hitting the entire document, right? And so, like, again, like there are different strategies in terms of how you chunk documents and how you create embeddings from them. This is just one of them. And it just happened to have worked well for me in different situations. But again, like definitely recommend not embedding entire documents. That tends to not work as well.
Thank you. And we'll close on this question for Databricks. Does Databricks retain the embeddings in its Delta Live tables or other areas? I'm not very familiar with Databricks. Let's get anonymous familiar.
Yeah, I mean, you don't have to. It's just like a scratchpad. I mean, you can store them as long as you want, or you can, if you choose to. It's just a checkpointing in this use case. But ultimately, it'll be stored in Pinecone and I think served out of there. Yeah.
Yeah, that's fair. And again, like if you look at the Pinecone, the Databricks pipelining strategy, right? Like you can choose which step of the pipeline is temporary and which one isn't. So basically you can say like, so for example, right, like there's no need, right, for the step where I just add IDs to the documents to be stored forever and ever, right? It's just like a transient step, right? So like I would probably in production turn that into a temporary step that won't be saved as a table forever and ever. In again, this case particularly, we do need the table, the embeddings table, to be saved just until the Pinecone connector can write that into Pinecone, and then part of that notebook can be deleting that embedding table after it's completed.
Okay, well, only 2 minutes over. Sorry if we didn't get to your questions. Again, remember, you can ask your questions to me, and I will share them with our marvelous host at amanda@pinecone.io. Thank you all for joining us, and a virtual round of applause for our host. Thank you, everybody, and we look forward to hearing your feedback.
Thanks, Amanda. Thanks, Titin. That was really fun.
Yeah.
Bye.
Thanks, everyone.
Bye.